Hi and welcome to MicroStrategy. My name is Michael Hoffmann and I'm working as a principal sales engineer for MicroStrategy Germany. In this video, I want to show you how you're able to transform a semantic graph of MicroStrategy into a relational data warehouse so that you're able to analyze the objects and their relationships with speed. But before we do this and before I show you live how you can do this, we need to talk about some concepts of MicroStrategy and what is the right way to implement this kind of solution. So we start with a semantic graph. What is a semantic graph? The semantic graph of MicroStrategy is something unique in MicroStrategy. It's the core, it's the heart of every MicroStrategy solution. And the semantic graph addresses all the objects and their relationships to each other that stand for MicroStrategy solutions, okay? And the semantic graph, on the other hand, is the basis for a single version of the truth. So in the semantic graph, for example, you have the definition of all the metrics, of all the facts, of all the attributes, the dossiers, the reports, the intelligent cubes, and so on and so on. So everything in MicroStrategy is an object, and all the objects are related to each other, if this makes sense, and the semantic graph is covering all these object dependencies. In other words, MicroStrategy works to 100% object-oriented and keeps track of all the dependencies between these different objects. The question is, why is it so difficult to query and analyze hundreds or thousands of object dependencies at the same time with speed? Okay, so if we take a closer look at the semantic graph, we can see that this concept of the semantic graph is very flexible, very elastic. This means it's possible to inject new objects over time, if the product is enhanced over time, into the semantic graph. It's able to inject new dependencies if we bring new products in the market into the semantic graph. So in other words, the semantic graph has a kind of object-oriented data structure that makes it possible to easily manage and relate objects of any kind to each other. And the semantic graph is optimized to get single objects, or let's say a few number of objects and their dependencies very fast, very fast. So the corresponding data model of the semantic graph is not a typical, let's say, reporting or warehouse data model with lookup tables, with fact tables, with a snowflake schema or so. The model of the semantic graph is very optimized on the usage of single objects or few objects and their relationships and to maintain these objects within MicroStrategy. Okay. So, and this is the let's say the challenge here, and this is the demand. Why is it so difficult to analyze, let's say, hundreds of metrics at the same time with all their coherences to facts and tables and reports and dossiers? You know, for example, you want to analyze, give me the number of metrics and the number of dossiers in 1 second that are related to a specific table, or let's say a specific view. Yeah, you can't answer this question directly on top of the semantic graph. Yeah, so this is the challenge we have, but we want to do this. And the question is, how can we do this? Okay, the answer is we can do this by using a new product component of MicroStrategy. And MicroStrategy has now Python embedded in MicroStrategy. So in MicroStrategy Workstation, you can run Python code directly against MicroStrategy's REST API. This makes it easy to work directly against the semantic graph. And the REST API provides all the functionality you need to work with any kind of object in the semantic graph. So you can query single objects, you can query dependencies between objects, and all this can be done using Python. Yeah. In MicroStrategy Workstation, as I mentioned, we have an integration for this kind of Python modules. But if you like, you can use other developing environments as well, because MicroStrategy provides a Python package called MicroStrategy IO. And this is the basis in order to use this kind of functionality and capabilities to work directly against the MicroStrategy REST API and the Semantic Graph. By the way, all the new products of MicroStrategy are using the same interface. So this means it's very robust, it's very powerful. If you would like to maintain objects, MicroStrategy objects with MicroStrategy Workstation, we're talking about exactly the same functionality. Okay. But how can we start our journey? So I think the best solution is we need to start our thinking from back to the front. So what is the kind of goal we want to achieve? And then we go back and think, okay, what does the REST API provide on functionality? What should we do? What can't we do? What doesn't make sense? Okay, so first, I think we want to achieve cool, fast, good-looking dossiers, yeah, in library where we have the option to analyze these coherences between all the different objects with speed. Yeah, in the best case, in less than a second. Okay, so I would like to jump in, I select a table, and then from the table, I would like to ask the question, tell me about all the facts, or the metrics, or the dossiers that are related to this table. And then I would say, I would like to focus on a specific fact. Now tell me what metrics, what dossiers are related to this fact, and so on and so on. So in other words, we need a kind of data representation, yeah, that we can use to put dossiers on top of it. So we need a kind of database structure, yeah, you can use, yeah. And if we leverage now Python with the new interface that's working on top of REST API, we can get all the information about these objects, yeah. And we need this information then, and then we can transform this information in a kind of data, let's say, structure or representation where MicroStrategy is able to analyze all these business coherences. Okay, so at the end, we want this cool and smart and fast dossiers in order to analyze all the objects and object dependencies. But at the beginning of our journey, we need to use the Python REST API, and we need to collect all the information of all the objects and the dependencies. Yeah, and here's one advice, one best practice from my side. It doesn't make sense, yeah, to do everything on top of the REST API if you're able to transform data and to build, let's say, analytics on top of data with Python. Yeah, because the REST API is for sure, because it's a REST API, it's slower, yeah, than doing Python operations directly in memory. Yeah, so this is my advice. Use the REST API only in order to collect the basic objects and their dependencies you would like to analyze later, and then do the rest with Python. Do all the transformations and all the preparations and the creation of all the data that is needed to populate your warehouse. Okay. Good. As I mentioned so far, we're using Python with the MicroStrategy IO package. The MicroStrategy IO package is a specific Python package that can be used standalone as well. Okay, so can you use your own, let's say, coding environment like Visual Studio Code or Visual Studio or Jupyter Notebooks. And yeah, you can use this then directly on top of the REST API. And from there, we transform the data from the semantic graph into a database model that we can work with. Okay, so this is our strategy. Okay, during the next live presentations, I will cover two options, yeah, to follow this approach. The first one is the easy one. I call it object level dependencies approach. Yeah, this approach works with the pure data that comes from the REST API. So the pure information about the objects and their dependencies. And this approach for sure is a little bit limited when it comes to, let's say, more demanding use cases. But then in the next step, I will cover a more powerful approach. And in this approach, I try to transform this data into a real, let's say, entity relationship model, like a data warehouse model, where we have lookup tables for all the different objects of MicroStrategy, a lookup table for metrics, for facts, for tables, for dossiers, and so on and so on, and the corresponding many-to-many tables that relate all the objects to each other. In other words, this is then, I would say, a very flexible object model in a data warehouse that we can use in order to analyze the semantic objects in the semantic graph. Okay, and then we take a look at two dossiers. I have prepared two dossiers that show the two options, and then you can see how it works in real life. Okay. Here you can see the result of the easy approach. Yeah? Here you can see the first option. And here's the dossier that is working on top of the data that I created in the first option. And you can see here the different level of dependencies, yeah, that I extracted from the semantic graph. And yeah, in this Sankey diagram, for example, you can choose an entry point. You can say, I would like to start from the table entry point. And then from the table entry point, you can follow all the different levels of dependencies, yeah, to analyze your objects and the dependencies behind those objects. So here, for example, you can see we have tables, and the tables are related to attributes and facts. The facts are related to metrics. These metrics are related to documents. Some of them are related to other metrics, and so on and so on and so on and so on. And you see here to the left, yeah, the number of tables. And if I would say I would like to choose this one here, this table, then everything is focused on this single table. And you can see there are facts and metrics and so on that are related to this table. By the way, if you want to see the details, the objects behind these levels, you can scroll down, and here you can see the facts, yeah, that are related here to this table that I choose for my analysis. Yeah. Okay. This approach is very, let's say, flexible. It is flexible, but for sure it's limited. We do not have here dedicated lookup tables for documents, metrics, and so on and so on. So this is here a combination of different object types on each level. But you can do a lot with this approach. It's easy to achieve. I will show you this a little bit later. But it's limited compared to the full data warehouse approach. Yeah? Another way to query this data is full text search. Yeah? So I'm starting a full text search here. You can see revenue. For revenue, we have facts called revenue, metrics, and so on and so on. I would like to limit on metrics. And then you see all the metrics that are related to revenue. We see the metrics here. I select one metric here, and you can see this metric is related directly here to a dossier or many dossiers. I scroll down, and you can see here the metric and the corresponding dossiers. But on the other hand, this metric can be related to other metrics. This is the complexity of the object model. It's not so easy. It's not so, let's say, clean, the structure, because objects can relate to other objects, and the object type might be the same. This is the complexity of the semantic graph. This makes it complex to analyze the semantic graph with, let's say, a typical reporting model on top of it. Yeah. If you would like to see the metrics here that are related to this metric that I select here, I click on this metric, and then you see here the metrics that are using this metric for their definition. Yeah. It's easy to analyze the data with that. Yeah, you have other options here as well, but I don't want to go into all the details of the dossier. But I think the approach is clear. We're working in levels. On each level, we have a combination of different object types. We have the dependencies between these object levels, and we are navigating through these levels. Okay, and now it's time to jump into my Python code. And here you can see the reference to the MicroStrategy IO package or library. I'm importing a function called full search. And full search is a powerful function you can use in order to get many objects of the same type. Full search has many parameters, so you can optimize your search results. You have many options to do so. And this is the main function I'm using in order to query the objects in MicroStrategy. As you can see here, I'm not using Workstation. I'm using Visual Studio Code, and I'm using the Jupyter extension. This makes it very nice, to code and to run blocks of code separately and to check your code and to debug your code. I can recommend to use Visual Studio Code and Jupyter here in combination. Okay, and now the code starts. I'm then iterating through specific object types. So for example, I'm start with tables, and then from the table, I'm searching for relationships to facts and attributes. After this is done, I'm querying all the facts, and I'm searching for relationships to metrics. Then I'm querying the metrics. Metrics is more flexible. Okay, a metric can relate to many other objects, to a report grid, to a bulk report, OLAP cube, another metric. This is the complexity of the object model. So metrics can relate to metric, that can relate to metrics, and so on and so on. And you will see later that in the second approach, that is much more powerful, I'm using recursive functions in order to consolidate metric to metric relationships so that it's easy for you later to analyze all the metric to metric relationships in one step. For example, from a dossier point of view or a table point of view, and so on and so on. Okay, after we imported the metrics, we query the attributes, and then after that, I have filled my lists of source objects and dependent objects. Okay, so I have then lists that give me all the object types, the object names, and the IDs of the objects, and this all for the source objects and the dependent objects. Okay, from there, if I have these lists, I'm creating a data frame. And this data frame then is a kind of virtual table where I have all the objects I need. And as I mentioned, I have there all the source objects, all the dependent objects, and their relationships. And this gives me a representation of all the objects that are relevant for me, for my use case, and the relationships between these objects. And then I'm writing this big table. Yeah, that is a data frame. A data frame is a kind of virtual table. I'm writing this to a CSV file. Yeah, and from there I can do whatever I like with the CSV file. If you like, you can import the CSV file directly into a database. But in my situation, I created a CSV file because I want to use this CSV file later for further data manipulation scenarios. In the next step, we will take a look at the data that we extracted from the semantic graph. Here you can see the CSV file that I imported into a database. And you can see we have these 6 columns, 3 for the source objects, 3 for the dependent objects, and for each object we have the type of object, we have the object name, and the source ID. And the source ID is the primary key of each object. Yeah, and here we see all the objects and all the relationships between the different objects. Okay, for my first approach, I'm using only this table. Yeah, I'm using only this table, and from this table, I would like to create all the dependencies and the visuals that you saw before when I showed you the dossier. So the question is, how can we use this table here in this database that was created using Python and the REST API to analyze the object dependencies in the way you saw before in my dossier? And now we step into MicroStrategy Workstation. Workstation is the tool for administration and for the schema implementing and for the architects to implement tables and facts and metrics and relationships and so on and so on. And what I did here is I created a logical table. Okay, a logical table. Why? You can see here the sequel of this logical table. And in this logical table, I'm referencing the table that we created first with Python. Yeah, this is the content of the CSV file. Yeah, but please remember, we are talking about object dependencies. So in other words, a dependent object in this table can be the source object for another dependent object. Yeah, this is important to understand because we have metrics, for example. A metric can relate to a dossier, but a metric can relate to other metrics as well. And this can be a dependency that goes over many levels. And therefore, I'm using the table that we created here with Python several times for each level, and I'm relating these tables to each other using a left outer join. I'm relating the dependent object from the first table to the source object of the next level, and so on and so on. Here the dependent object to the source object of the next level, and so on and so on. The left outer join is important, otherwise you won't get all the relationships. And then we have a logical table in MicroStrategy. You can see here, this is the result here that we have here. And we have all the columns here from level 1 to level 2 to level 3 up to level 10. Level 10 is absolutely enough here for my demo, because in tutorial we do not have more levels for navigation. And yeah, then you can model your attributes on top of this logical table, and then you have your data set, and then you put an intelligent cube on top of this data set, and then you have really a high performant data structure you can use for your dossier in order to do the things you saw before in my example, where you saw the dossier and the navigation on all the different object dependencies. Just for a clarification, here we are back in the dossier you saw before, for the navigation through all the different levels. And here you can see the data set that I created from this logical table. For each object, we have the single object with the name and the ID, and then a corresponding object type. And here, for example, in the Sankey diagram, I'm using the types, so L1 type, L2 type, and so on and so on. But I renamed the name here of the attributes so that you see here level 1 to level 5, and so on and so on. Okay, so this makes it very easy to leverage the data that we created here by using this mechanism. Here, for example, in this table, you can see L1 object, L1 type, and each object has a name and a corresponding ID. That's all the trick. And now we come to the second approach. This second approach is much more flexible, but it's much more demanding on the other side. This means we need more effort in the data preparation phase here with Python to achieve the data structure we want to have. We want to achieve a kind of data warehouse model in a database where we have dedicated lookup tables for attributes, metrics, facts, documents, and so on and so on. But this is not enough because we need to relate the objects to each other. This means we need many-to-many relationship tables, for example, in order to correlate metrics to dossiers, because one metric can be dedicated to several dossiers. One dossier can have several metrics. So for all the dependencies we have many-to-many relationships, okay? And this is not a typical data model that we are using here with MicroStrategy. In most cases, we're talking about star schema or snowflake schema. This is much easier. In this case, we need to transform an object-oriented approach onto a database approach with dedicated lookup table and relational table. Okay, but this is not enough when it comes to the complexity. Complexity is even higher because metrics are special objects. Metrics can relate to metrics, can relate to other metrics, and these metrics can relate to other metrics. At the end, the final metric is related to a dossier. And we do not know how many levels do we have during the navigation between all these different levels between the metrics. And maybe we have customers that have thousands of metadata objects and thousands of metrics, and maybe they have, let's say, 30 levels between metrics. So in other words, the approach you saw before is a little bit limited because you need to think about, okay, how many levels is the maximum? And then you tweak the solution to address the maximum of levels that we have. The second approach is independent of the kind of levels we have between the different metrics. And the trick is we need to consolidate. We need to consolidate the metric to metric relationships. Okay, so in other words, I'm doing a recursive search from metric to metric as long as needed in order to synchronize or consolidate all the relationships into one level. Okay, this is the trick. And this needs to be done with Python. And as you can see a little bit later, Python is the perfect fit, to do even this complex data preparation task where we need to implement recursive functions that call themselves in order to process these coherences. Okay, good. We have here an example that leverages the data in the data warehouse. You see here, this is one of many navigation paths. Okay, so here on this task, or on this page, we can navigate between documents, metrics, and facts to tables. And then we have the corresponding documents and metrics and tables here. By the way, I'm calculating here the corresponding objects that are related to these, let's say, object types we have. So, for example, we have 229 dossiers here on this page. And for example, this dossier is using 2 metrics, 2 facts, and these facts are related to 17 tables. Same as here with the metrics. So for each object, you see the counts of the relationships to the other objects. Okay, you see here 288. So what does this number stand for? This is the total number of dossiers, but only 229 have this kind of navigation path. Okay, so from documents to metrics to facts to tables. Okay. Why am I talking about navigation paths? Because you have many of them. You have the option to navigate from a table to a fact to a metric to a dossier. But on the other hand, you can say, no, I want to navigate from a table to an attribute, and then from this attribute to a dossier. Or I say, I would like to navigate from a table to an attribute, and from there to a fact, to a metric, because this metric counts the IDs of this attribute, and this metric is related to dossiers. In other words, we're talking about navigation paths. And here in my dossier, you can see I've implemented these different navigation paths. Okay, see here, this is the navigation path from document to attribute to table. And here, this is the navigation path from document to metric to fact to table. And now you're absolutely free for your analysis. So for example, you can say, I would like to search for sales tables. You can see here we have a table called item amp sales. Click, and then you see the table and the corresponding metrics and the corresponding facts and the dossier. I would like to focus on, let's say, this metric. And now you see here, okay, there's one dossier that's related to that. Now, I think it's clear what you can do now. The Sankey diagram is also interactive, so you can select, for example, in the Sankey diagram, you can say, okay, I would like to focus on units sold, on this fact, and then everything is recalculated less than a second. And you see, okay, these units sold are used from 90 dossiers. We have 8 metrics. Let's take a look at this dossier, and then you see, okay, these are the metrics here. This is the fact. These are the tables correlated to this. Okay. Moreover, you can start your search, because now we're very flexible. You can start your search with the global filters. For example, here, cool feature in MicroStrategy, pop-up filter. And this pop-up filter, this is not an info window. This is not an info window. Okay, so this is a pop-up filter that's part of the global filter panel. And here, for example, I'm searching for tables with a lot of relationships to attributes and metrics and facts at the same time. So for example, this one here, okay? And I click apply. And now we see, okay, here is the dossier, here the metrics, the facts, the tables, and so on. And if I would like to see the other navigation path, so for example, from this dossier over the attributes to the tables, I just need to switch, and then bam, I have the information and we're done. I think it's clear. We have now a lot of flexibility in this model, and it's up to the designer of the dossiers to use this kind of navigation paths. Okay, now let's jump into the database schema. yeah, that is generated by my Python script. I will show you the script at the end because this is the most demanding part of the solution. First, we take a look at the data, yeah, that is created by this script. Okay, see here we have dedicated lookup tables here for the MicroStrategy object, so for attributes, bulk reports, documents, dossiers, and so on and so on. So for example, if I take a look at attribute, you see we have the object type, the name, the attribute ID. Yeah, and same with metrics, same with facts, and so on and so on. As I mentioned before, we have to cover the relationships between these objects, and we are talking about many-to-many relationships. Okay, it's not so easy compared to a snowflake schema or the star schema. So we are talking about many-to-many relationships. So for example, you see here, these are the tables that cover these many-to-many relationships. So for example, we have here, for example, we have a table attribute. Yeah, this means we have the table ID and we have the attribute ID. Yeah. Additionally, I populated here the info columns as well, but they are not needed here for the approach. Important is the relationship between the different IDs. Or for example, metric and attribute. Metric and attribute. Yeah. So an attribute can be the source of a metric. So for example, if you would like to count distinct elements that come from a metric, yeah, this is the dependency. Okay, so sales by brand, for example. Yeah. Okay, so we have the lookup tables, we have the relationship tables, and this all together is based on the entity relationship model. So if we take a look here at the attributes and we go to the entity relationship model, you can see here's the attributes, yeah, and the attributes are then related to all the different relation objects, yeah, and the relation objects is always a combination of the both IDs, yeah, that describe the relation. So for example, the attribute ID and the document ID. Okay, so this is the trick. Okay, and now we want to take a look at the schema that I developed in MicroStrategy in a project, in order to use the data that I extracted and transformed via a Python. And yeah, this looks very easy. You have some attributes here. Each attribute is related to a MicroStrategy object, is related to the corresponding lookup table. And moreover, we need additional attributes that describe the relationships between the objects. And these objects are here. So for each relationship, for example, between table and fact, we have a relationship object because this object is related to the many-to-many relationship table. Yeah, and as an example here in this object, the attribute has two parents, the table parent and the fact parent. Yeah. Same here with fact metric and so on. So the approach is always the same. Yeah. Here we have only attributes that are related to the many-to-many relationship tables. And these attributes have parent attributes, and the parent attributes are the attributes that are related to each other by using this table. Yeah. And with that, you have all you need to use this data for your analysis. Something is important to analyze the coherences in the right way. Please think about the option that you can navigate from one object to another object via different navigation paths. So for example, from a table via fact and metric to dossier, or from a table via attribute to dossier, or from a table via attribute, via metric to dossier. So 3 different options, yeah, to navigate from a table to a dossier. And if you want to force MicroStrategy Engine to do the right joins, to work with the right objects here, for joining the data correctly, because you have many navigation paths, many join paths, because we are talking about many-to-many relationships, yeah, it's important that you integrate the right relationship attributes into your query. Yeah, so for example, quite easy, you want to navigate from tables to dossiers. You want to understand the relationships between tables and dossiers from the perspective and the navigation path, table, fact, metric, dossier. Okay, and therefore you build a query by using table fact, metric, dossier, and additionally, you integrate, table fact relation attribute, fact metric relation attribute, and then metric document dossier relation attribute. And this forces the engine to do the right join here for this navigation path. Okay, this all. I think if you have done this once, it's easy to repeat this. It's always the same. Yeah, the options and the approach is always the same for all the different navigation paths that you have. Okay, so for example, if you would like to navigate from a table to an attribute, and then from an attribute to dossiers, and you want to do this for all the tables, all the attributes, all the dossiers at the same time in order to understand the numbers behind these relationships, you can build a query using table, attribute, dossier, but please integrate table attribute relation as well and attribute document dossier relation as well, because then the engine knows how to follow the path from the bottom to the top. The reason is the engine has several options to do this. The engine is not able to understand this. This is not a Snowflake schema. This is not a star schema. In Snowflake and star schema, it's much easier, and we do not have this many navigation paths between the different attributes and hierarchies in our model. Okay, one additional tip you can use in case you say, I want to give this in the hands of the customer. I want to provide the customer an easy to use object model to leverage this capability. And you want to hide here the concept of relational attributes and standard attributes and so on and so on. The approach is easy. You just put a view layer on top of the tables that we created before. So we have the lookup tables, we have the many-to-many relationship tables, and then you can put a view layer on top of it, and then you model some additional attributes on top of this view layer, and then you're done. And this, for example, this here, I did this here for some of the navigation paths. So for example, from table to attributes to documents, and these attributes are linked to a view, and this view is part of the view layer that is working on top of the lookup tables and the many-to-many relationship tables. And now we come to the last element, but the most important element for the demo, the data transformation part that transforms the data that comes from the REST API into a database model that we can use to query the objects. You saw the model before, the lookup tables, the relationship tables, and the dependencies. But this needs to be created with the data from the semantic graph. Okay, I think you remember in the first example, I used this Python script to extract the data from the semantic graph, so all the source and dependent objects, and we're using exactly the same data. So no need to query the semantic graph again. We have all we need in this data extraction, and this is a starting point for us. Let's take a look at this data extraction before we go on with the code. So here we see the data extraction CSV files. We have 6 columns: source object type, source object name, source object ID, and the dependent object type, object name, object ID. So in other words, we have the relationship between objects that are used by other objects. And in the script you saw before to extract the data, I focused on specific source types. So for example, table, fact, metric, attribute. And from there, I analyzed the relationships to other object types. So for example, report, OLAP cube, dossier, and so on and so on. In other words, in this file, we have all the objects and all the object relationships that we need to create the overall warehouse schema. But it's a little bit effort, to work on this data and to prepare this data and to relate this data in the right way. And this is the next step I want to show you. By the way, we have around about 8,000 relationships here that I extracted from tutorial based on the focus of my demo. Okay, now let's get started. So the first step, I read in this data into a data frame. I drop a column that is not relevant. There's an additional column number 7. This is an index column, but I don't need it, so it's gone. Okay, so we have only 6 columns. The source columns, the 3 source columns, and the 3 dependent columns. Okay, in the next step, I filter this data. So I use this table that is now part in a data frame, and I filter this data in that way that I say, I would like to get only the relationships between metrics and metrics, okay, because I need to consolidate these relationships. I need to consolidate these relationships with the recursive function I mentioned before. Okay, so here in this data frame, then we have all the relationships between metrics and metrics. And in this data frame, we have only the data of metrics that do not relate to other metrics. Okay, here you can see a good scenario of using data frames. Data frames are so powerful. You can filter, you can join, you can union, you can do so much with data frames. It's the perfect fit for data manipulation, but you will see more during the script here. Okay, the next step, I need to create my lookup tables. And for this, I first create a master lookup table. The master lookup table is the union of all the source objects and all the dependent objects. And after I unioned this object, I drop all the duplicates. So this can be done so easily with Python. So first I extract only the source objects with the 3 columns. Then I extract all the dependent objects with the 3 columns. Then I rename the columns, yeah, so that we have the same column names in both data frames. And then I concat. This is a union. This is the same as a union in SQL. And then I concat the data frames. And then I say, okay, drop duplicates, and then the duplicates are gone. Yeah, and then I reset the index. This is not a must, but I did it here. Okay, by the way, how fast are these procedures? Okay, you see here, I now run this code here, only this block of code that imports the data and that creates the 2 additional data frames with the filter condition. So how long does it take to load round about 1 million rows? Or not 1 million rows, and this time it was only 8,000. Yeah, okay. So 2.5 seconds. 2.5 seconds to read the file with almost 8,000 relationships. And from there, we extracted the metric-to-metric relations and the master metric relations, as I mentioned before. In the next step here, as I described, we union these 2 data frames here, where we extract the source objects and the dependent objects, and then put them all together into one single lookup table. And this one single lookup table, then we filter, we drop the duplicates. So in other words, we get only the distinct values. How long does this take? So click 0.8 seconds. So not a second, yeah, to do this. So it's so fast. Okay. Next, I create the lookup tables. And the lookup tables I create on top of this master lookup table that I created before. And on the master lookup table I created before, I select only specific object types. You can see here lookup table, for fact, for attribute, metric, report, byte report, and so on and so on and so on. And how fast can we do this? Okay, not a second, yeah, to create all this. Okay, next. Now we have all the lookup tables. Next step, we need the relationship tables. Okay, so for example, the table that relates metrics to dossiers, or fact to metrics, and so on and so on. And you can see here, I'm creating these relationship tables based on the master table that I imported, and there I use some filter options here, yeah, on the object type in order to create these dependency tables. How long does it take? 0.1 1 second. So it's so amazing fast. This is the reason why I recommend to do as much as you can with Python and not on the REST API. Extract the main data you need on the REST API with the main relationships that are relevant, but everything else, do it in Python, do it in data frames. Okay, now we talk about the most complex part. The problem is that metrics can belong to metrics, can belong to metrics, that can belong to metrics, and we need to resolve this. Yeah, otherwise it's not easy to analyze these coherences. Okay, how can we do this? Please take a look at this part first. Okay, so we are using the master metrics relation table. This is the table where we have only metrics with dependencies to other dependents that are not metrics. Okay, so metrics that are used directly, let's say, from a dossier or report, and so on and so on. And we iterate through these metrics, and we remember for each metric what is the dependent that is related to this. I call this master metric. A master metric, in my case, is a metric that is related directly to a dossier or a report, but not another metric. Okay, so for each of these master metrics, I dive into this function that scans the dependencies of this master metric with all other metrics that might be related to this master metric. Okay, and therefore we have this function, and you see this function here. So in this function, I'm scanning the relationships that might be there from this metric to other metrics, and if there is a relationship, I create a new row for the relationship table. Okay, but we have different relationship tables. We have relationship tables from metrics to reports, from metrics to documents, dossiers, from metrics to OLAP cubes, and so on and so on. And therefore, we need to distinguish between these different types of relations and the different relationship tables or corresponding data frames that we have here. Okay, so in other words, we take the dependent from the master metric, we scan the child metrics relationships, and if there is one, then we create an entry, an additional row, and we put this row in the right relationship table. And with that, we are able to consolidate this. Unfortunately, a child metric can be related to another parent metric, and therefore we need to use this function in a recursive manner. So in other words, this function calls itself, but now with the next level of navigation, so with the metric level, with the child metric that was related to the master metric that was the entry point for my recursive navigation here. And if you do this, then you flatten all the dependencies, and no matter how many relationships you have, how many levels you have, everything is here consolidated together, and this makes it easy. And then we are done with the metric. Okay, after that, we need to make sure that we do not have any duplicates in our generated relationship tables, because this might be, because of the recursive dependencies that we are following here. And we can remove these duplicates if there might be any. We can remove them easy by just saying here drop duplicates, and then we're done. Okay, so how long would it take to run this function? Okay, with the recursive analysis, click. Okay, and you see here all the metric dependencies, all the recursive dependencies, 9 seconds. Okay, so this is, let's say, the most, this is the part that takes the most resources here, but 9 seconds is nothing, if you navigate all these recursive dependencies here through all the metrics, and so on and so on. Okay, the last step, we drop the duplicates, not a second, and then the next step, we create the lookup tables, the files for the lookup tables, and we create the files for the relationship tables, and then we are done. We concatenate everything here together, and Let's click. How long did it take? Oops. And we see not a second. Okay, so all the files are generated. Okay. The final question is, how do we import the CSV files into the database? You have two options. The first option is you use an universal database management tool or any kind of database management tool. I like dbeaver a lot. This is really the perfect fit for any database, and it has powerful import capabilities for multi-CSV file import. So for example, here I have a task configured with all the relevant lookup tables and many relationship tables, and we can import them in one step and update the data in one step in the database. That makes it very easy. If you have a different database, no problem. dbeaver as an universal database management tool can handle connections to any kind of database. Okay. The other option would be to write the data directly from Python into the database. You can do this too by using different SQL packages or SQL libraries, but please keep in mind that it makes sense to insert only a small portion of rows at the same time and then do a commit. And after that, insert the next portion of data and do a commit. So if you insert, let's say, 1 million row and then do a commit, it might take a long time on the database. Yeah. And the better approach is to say, okay, every, let's say, 10,000 rows or so, I do a commit and then I inject the next portion into the database. And if you do this, and you can do this with Python easily, then you have a good performance and then you can inject the data directly into the database. And with that, I'm at the end of my presentation. I hope you enjoyed this little journey with me. I think you saw that the semantic graph of MicroStrategy is really powerful, yeah, and it makes absolutely sense to have analytical use cases on top of it, yeah, to analyze the objects, their coherences, the usage of these objects. And there are many use cases where you want to analyze on top of the complete data volume of these objects, yeah. And I think you saw that the REST API, the semantic graph, is not, let's say, the data structure and the interface to query all the objects and all the dependencies at the same time. So this is not the usage of the semantic graph via the native interface, that can be leveraged by the REST API. But with the usage of Python and the new MicroStrategy IO interface on top of the REST API, you're able to transform this data into a kind of data representation that makes it easy to analyze the objects and the dependencies in a very powerful way. Yeah. What I showed you here in this demo are some examples, and I focused, let's say, on some of the most important objects of the semantic graph. There are many more for sure. So for example, filter objects, prompts, data sets, and so on and so on. And this can be added to the scenario. My intention was to show you a kind of approach. Yeah, how can we use the data? How can we transform the data? How can we do it in a flexible way? How can we do it in a more easy way? This was my intention, to show you the capabilities that are there, but it's up to you to use them and to, let's say, optimize and focus them on your specific business needs. Thanks a lot for watching. I wish you all the best. Bye.